Excited to be here and talk about this topic. And currently sharing my screen. Please let me know if you can see it.
Yeah, I can see your screen.
Perfect. So the plan is to go over exploring the NLP fuzzy matching algorithm, and I'll just give a brief introduction about what is fuzzy string matching, where are the applications, and then dive into a couple of very commonly used algorithms. There are a lot out there, and that would be covered in the other algorithm section. I'll just name them, then I'll do a example with a real data set, and I'll show you how things work. I believe Sapphire will share this. If somebody is interested, this link is available, and I believe Sapphire Rishika will share it later on if you want access to the notebook.
Yeah, could you want to share that now? Actually,
yeah, I can share it. So no. Give me 1 second. This is the link. And I can paste it in the chat, correct?
Yeah, you can. Thank you.
No problem.
Thank you. I can see it now.
Yep. So I'm going to start. So fuzzy string matching or approximate string matching is basically a method to find strings or text or words which match the pattern approximately with some probability. So the algorithms that work behind this basically identifies the likelihood that two words are like a match to each other, a true match to each other based on some criteria. So for example, let's look at this Microsoft here. I just spelled out 5 different ways of Microsoft Corporation. And the idea behind string matching is all of this should, if I want, then it should ideally represent this whole Microsoft Corporation. So that's the whole like idea behind fuzzy matching. It's better to do it probabilistically rather than finding a true exact match. Hence the name approximate or fuzzy. So as you can see, other than like checking spellings, fuzzy matching has a lot of other application, and like de-duplication of records, master data management, which is like you manage all your data and you don't want duplicate records there. You want to keep track of what is the unique value. It can be also used for plagiarism detection. It's used in DNA sequencing, bioinformatics, spam filtering, content search, so many different things. And there are I will be discussing very simple algorithms, but there are complicated ones which you can pair up and get to all of these wonderful applications. That being said, jumping on to the algorithms that I will be discussing, the most common method of fuzzy matching is doing an edit distance metric. And that is basically telling how different two strings are or two words are by counting the number of operations that I would need to do to go from one word to the other word. And I'll show you with some examples what I mean by number of operations or how I count the distance or what kind of operations that can be. But basically, you would be calculating, if I go to this example, if I take this entry 03, which is Microsoft Corporation, and I want my correct value to be Microsoft Corporation, then there is, like, this is basically an equal match. So the distance would be 0. But for others, there has to be some kind of distance to come to this correct value. And that is what these two matrices called Levenshtein distance and Damerau-Levenshtein distance are used to calculate. And Levenshtein distance is the most common one that is used across fuzzy string matching. The other two that I'm going to cover today is called BITAP algorithm and n-grams. Now, BITAP algorithm basically tells you, like, a part of the whole string is approximately equal to the string that I want to match. So again, there is Levenshtein distance used to figure out how closely they match each other or how dissimilar they are, but it can't compare something which is like bigger. It has to be either substring or like the entire string. And n-gram is a technique which is very popular in natural language processing. And it is a probabilistic method which is based on Markov process. And not going too much into detail about Markov process, but it basically what it does is if you give a sequence of text or a string, it tries to predict what would be the next item. And the better information it does, the better correction to the word or closer to the correct value you can get. So let me next dive in to the edit distance matrices, the Levenshtein and Damerau-Levenshtein. And as I said before, this basically measure the number of edits that I would need to make to transform one word to another. Damerau-Levenshtein is very similar to Levenshtein, so I'll first cover Levenshtein and then tell you what is the difference. So the techniques that is used to transform is insertion, deletion, or some kind of replacement of the letters or the words. For example, if I want to calculate the Levenshtein distance of the word ARKS, which is spelled as IRKS, and I want to see what is this distance between this word and risk, then the Levenshtein distance is 3. And how that works is you start with ARKS in your algorithm, and what happens first is to compare it with risk, it first starts with deleting the letter I at position 0. So that is one of the techniques here, which is deletion. And since it performed one technique, the distance is +1. And then now from here, I is deleted. Now we have RKS. So now what it does is it replaces K with I, and hence another +1 distance is added. It goes on, and now I have RIS, and it compares with RISK. It sees that I need to insert K here. So it inserts K, and it adds another distance. So hence, the distance between ARCs and risk is 3. Now, the difference between Levenshtein and Damerau-Levenshtein is that it allows for another technique called transposition. And this comes in very handy. It obviously does insertion, deletion, replacement, same as Levenshtein, but it also allows transposition. So going back to the example, how that works is, now it compares args to risk. And the first step is it sees that I can just transpose the first IR to get to RI, and it transposes that, and that adds the distance +1. In the next step, the algorithm sees that I already have RI here, and to get to risk, I just need to do another transposition. And when it does that, the distance is 2. So I need only a minimum of 2 distances to go from args to risk when I'm using Damerau-Levenshtein. So in this case, the distance is 2. So that is why I have here as if I do a distance for Damerau-Levenshtein, it's 2. But for Levenshtein, since it does not have the transposition, it needs to go at least 3 steps to do this comparison and get to the word I'm looking for. I will, again, if you have any questions, feel free to put it in the chat. I can come back to it at the end of the talk. But I will move on a little bit with this. Now, Levenshtein distance has the properties which it always follows. As I said, if it is 0 only and only if both the strings are equal to each other in distances and as well as all the words that you're looking for. It is at least the difference, so the least amount of difference would be the size between the 2 strings. And the most difference would be the length of the longest string if you're comparing strings of different sizes. And there is an inequality which Levenshtein distance always maintains, and it is called the triangle inequality. And that is just if it is comparing a distance between 2 strings, it would never be greater than the sum of their distances with a third string. It's similar to how we studied in geometry in triangle. So this not some extremely important to code, but these are some good things to remember. I thought of doing giving a little bit of simple math background as to how the Levenshtein distance is calculated. And string between A and B is always length of A. Like it always tries to calculate the Levenshtein distance between the length of string A and the length of string B. Where there is this definition where it says what should be the minimum value and what should be the maximum value. And this +1 is basically the same as I talked over here. It's adding the distances depending on what the differences in the strings are. So this portion of math is basically a more formal mathematical representation of what I discussed on the top here. So now let's do some coding, and I coded up this function which just calculates Levenshtein distance between 2 strings, S and T, in a recursive way. And if I run this function, I do it on the same example as args and risk, I get the distance is 3, which is what I want. So my function is correct. However, these are very small words, and in real life, I want to compare like not just 2 words, but maybe bigger words or maybe sentences. So I just wanted to check how it is doing on time, and doing it this way, the function that I wrote, it's taking like almost 30 seconds to compare these 2 words, which are Microsoft and Microsoft Corporation, which was in the example that I had, which is a lot of time, and we don't want that. So this is extremely slow. And if you're trying to do this on your real data, you would not use this algorithm. And this is a very naive implementation of it. So I just wanted to point that out, that this is not what is generally used in the algorithms behind the picture, behind the scenes of any application. An efficient way is to do it using an iterative process and a matrix implementation. And if we do that and implement this function over here, which is basically it traverses through the matrix, it forms a matrix and then tries to compare like row-wise and column-wise distances, as you can see, row-wise and column-wise distances, and it basically implements the three techniques that I discussed, whether it is deleting or whether it is inserting or whether it is substituting. So since it is doing a column-wise and row-wise comparison, it is much more faster. And I can show you how faster it is. It's the same example of Microsoft and Microsoft Corporation. The previous simple recursive method was taking almost half a minute, but this way it takes pretty much 0 seconds. So this is much more faster version of calculating Levenshtein distances. And again, these are simple implementations that anybody can write it, but there are nice packages out there, which is one of them is Jellyfish, which I have used here, which already has Levenshtein distance implemented. Libraries like NLTK, which is very useful in NLP, also has Levenshtein distances, and you can find a lots of other packages and algorithms out there which can calculate this distance much faster. That being said, wanted to check next how Damerau-Levenshtein distance works. And if we just import this cool package, which has all these fuzzy string matching algorithms available, I just try to find what is the difference between, what is the distances between the words arcs and risk for Levenshtein and Damerau. And as we did it before, we get the same 3 and 2 back. And again, as I said, if we just import this and apply it in our code, the time taken is much, much smaller than actually me writing everything from scratch. So that this is you can check out this package and do some simple hands-on exercise. It's pretty cool. So next, we move from edit distances or edit distance matrix to something called BITAP algorithm. And this is a little bit different in the sense BITAP algorithm works using bit arrays. And bit arrays is very, how to put it, it's much more faster in the computer world because you are assigning, you're structuring everything in a nice format, and you're assigning and you're doing bitwise calculation. You're converting everything to bits. So it is very fast, and it is also known as shift or at shift and, just because it uses and or operations to get to this approximately equal distances. And the distance, again, approximately equal distance is again calculated by the Levenshtein distance, which I discussed. However, the search of how close these words are, or how can I go from one word to another, that is done using bit arrays. And I coded this up using a similar implementation, which I found in Geek for Geeks. But this is basically the behind the screen code that works for BITAP algorithm. So first, it starts with a BITAP search, which is what I was saying, making use of the bit array and assigning it and doing some kinds of searches, taking the edge cases, figuring out whether I should be doing a shift or shift and there is a very nice explanation of the algorithm on this website, and I have the links in the reference section, so you can look that up. But this is, so what first is does is if I want to find a pattern, so let's say I have this input, right? I want to compare how this text, which is women who code, and another text, which is code, if they match with each other or not, or how closely they match each other. And if they do, then I want to find at what index they are matching. It's not necessary to find, we can just say yes or no. However, we can see if it matches or not. So I took this as an example, and using this code that I wrote up, if you see, if I do this text and this pattern, I implement this algorithm here. It says pattern found is at 8, which is code is found at position 8 of the text that you have given. Now, if there is another text, which is like, you are awesome and you are amazing, it says no match because it considers this entire thing as a string that has to be compared to you are amazing. So these two do not have any match just because there is no substring. This substring is not matched to this string. Now, if it would be you or are or you are together, then yes, you would find a match, but these two have no matches. And this function basically, as I said, tries to find the pattern using the BITAP search, which uses the bit array here and does some simple and or calculations. This is the or part, this is the and part. Okay, so this is how the BITAP algorithm tries to do fuzzy matching between two strings. The last one and the most, I would say, advanced version of this would be the n-gram algorithm. Now, n-gram basically tries to set values generated from strings or words or characters by pairing sequentially these occurrences of these words. Now, when I'm using an n-gram algorithm, the goal is to compute the sequence of characters because I want to predict what is my next character going to be. So if I say, let's say, give an example like set off. So every time, if I'm training my algorithm to always give me off whenever it sees set, something along these lines. I'll explain it better with an example. But behind the screens, what I was talking about Markov model is behind the screens, it works on probabilities, and conditional probability is what is predominant in n-gram. So we all know what conditional probability is. It's like probability of word 1 given word 2 is given by this expression. So now imagine there are not just 2 words, but there are 4 words. So then this probability on your right hand side of the equation increases. It's probability of word 1 times probability of word 2 given word 1 appears, and then 3 given word 1 and 2 appears, and so on and so forth. So if I have like n characters or n words or n sentences, it's going to be the same principle. It's just going to be a product of all these probabilities given if this word appears or that word appears. But as you can imagine, if like with 4, I'm already seeing this many terms. So if there are, as the number of words or characters increases, there is going to be way too many possibilities for anyone to just go there and calculate. So the best way to do it is to use Markov process. And what it does is it doesn't calculate exactly what the probability is, but it approximates what the probability is by kind of getting what the estimating the maximum likelihood of that word appearing. So again, it goes back to probabilities and maximum likelihood approaches. And instead of us calculating each probability one by one and multiplying it together, what Markov model suggests is I am just going to take a word and find out what is the maximum likelihood that this word appears next to the other one, or next to word 2, or next to word 3, and then I'm going to multiply that. So that makes the algorithm much more easier and faster to calculate. So let's take an example, and that would be just easier to understand. And I'm going to provide this set of words, and I want to compare all of these words, and my correct word or correct sentence that I want to compare all of them is this one. I want to check how similar or closely related the company name is Microsoft Corporation is to all of these different variations. And before I do the similarity checking, the one thing I wanted to go over was how this n-gram technique works. Is if you just take TF-IDF vectorizer from scikit-learn or even count vectorizer and convert any text into vectors, there is a possibility, there is an option of suggesting what kind of n-grams you want. Do you want unigrams, which is 1 or 1? Do you want trigrams, which is a combination of 3 words? Do you want a minimum combination of 1 word and then maximum combination of 10 words? So you can change that depending on what the model is going to be used for. So here I have shown 3 different examples with the same corpus bunch of words here. So if I just do unigrams, then what it does is it takes this entire thing and tries to break up all of these, each word, because I'm saying that my minimum break should be at word level. So it tries to break up all of them into one single word. If I say trigram, then as you can see, all the combinations are a combination of 3 words, all the possible combinations that this can do out of this, all of the words present here. So if I go beyond, if I say it can range anywhere between 2 to 5, then you can see the number of combinations increase a lot. So depending on what is required, I can change my n-gram range, or I can deal with just trigrams. And that is something that's up to the model or up to the use case. So now let's see how it does fuzzy matching for using n-grams. And there is another, as I was saying, there are lots of algorithms available, packages available already for doing fuzzy matching. And this is one I used here to just check the n-gram technique. So importing all the libraries that I need, and I'm going to use the same corpus of words here. So I take this, and this is okay, let me take a step back. So since I want to compare all of these to just one entry, it's easy to do it whenever there is one entry and the number is small. However, what I want to ideally do is make a Cartesian product of these things. So I basically want to compare this entry to the clean word and see how close they are. Then the next entry to the clean word and see how close they are. So you can imagine that this number is going to be huge if there are lots of combinations that I need to compare, or there are even multiple words that I would need to compare here. So the best way to do is to, well, the fastest way, if I want to do it, is to get like a Cartesian combination of all of these words. And that is what I did here. And you have to always remember that this will expand very quickly as the number of words increase. So this is how now the Cartesian product looks. So it is just going to compare each of these entry with the correct value. So now that I have this list ready, I want to see what are my Levenstein distance scores and what is my trigram distance score. So remember, trigram is when I'm looking at triplets of words. What is my trigram distance score? What is my Levenstein distance score? And there is another one that I would want to look at, which is the cosine distance, which is again very applicable for finding similar words in natural language processing. So I basically find out what these words are, and this is the result. So these were my input, or unclean data, if I can call that. And this is my clean data that I want to compare it with. And this is my Levenstein distance score. So I should tell this that if it is closer to 1, then these are most similar. If it is closer to 0, then they are very different from each other. So as you can see, this one has the highest score just because it kind of contains almost the entire value of the correct clean data that I want to map. So basically just telling you all the different ways that one can match words and what is the logic behind it. So behind the screens, it's always some kind of a distance matrix, and mostly Levenstein. Or if I want to do cosine, that's also possible. Next, I want to show you how this can be used in a real data. And I downloaded this data from Kaggle, and the link is here. If you click this link, you can easily get the data. I have also put the CSV file on the Git repo, so it's available there as well. And the data that I'm going to use is just a data that contains 2 columns for room type description. And column 1 is basically room type description from Expedia. It's a website that has booking details of hotels. Another is booking.com. And the aim here is, if I have a data like this, then which algorithm would help me kind of figure out how close or how similar these two values are. So pretty much when me as a human, I see deluxe room, 1 king bed and deluxe king room, I can immediately understand, yes, these are same things. But when I'm putting in code, then these are not two same things. But I would want my algorithm to work so that these are identified as similar things, if not exactly same. So that's the aim here. And I have used two different packages to kind of show the use cases. One is called Fuzzy Wuzzy. Again, link is here to download it, install it, and the other one is called Fuzzy Match. So there are different ways of getting to these ratios or how close these values are. So the first one is I compare the entire string. So I would compare standard room, one king bed accessible to standard king roll in shower accessible. So the entire string, and then tell how similar they are. Another method I can do is calculate the partial ratio, which is just maybe compare parts of the strings with each other. The other option is it's called token sort ratio in the library, in the module. What it does is it ignores which order these words are appearing. So if king bed is appearing at the end or at the beginning, it would kind of ignore that and it would say, okay, it doesn't matter, it's going to be the same. And the last one that is available is token set ratio. And what it does is it ignores the order as well as it ignores if there are duplicate words present. So what that means is going back again to this example, let's say, yes, this one. The king appears twice, but the king appears only one here. Again, as a human, I can immediately go, yes, these are same. But I would want my algorithm to also do the same and not consider that there are two kings or in which order the king and the room and the bed appears. So that is what the token set ratio is doing. And I can also do a trigram similarity, which is what I discussed just a little bit earlier, is split the strings into n grams of length 3, and then figure out what distances are between them. So what I did is I put all of these and put this result in the data frame. And so for these values, it should, the closer the matches, the closer to 100 or 1 basically it is going to be. For trigram, it's again the same. The closer the matches, the closer to 1 this value is going to be. So in this particular, so you can, I have listed out all the 4 methods along with the trigram that I discussed, and full ratio is always going to be lower than any of the other ones just because it is trying to compare exactly, well, not exactly, it's trying to compare the entire string and in the same order and with the same words. So it is lesser than the partial or token versions, even the trigram versions. But in this particular case, it turns out that if I do this last token set ratio, which is ignore duplicate words, ignore the order of words, then I get the most similar human-like match. So for this data set, I would just go with applying token set ratio to find out which values are closest to each other. Okay, so that kind of brings me towards the end of this. And as I mentioned, there are lots of other fuzzy matching algorithms available. Even in edit distances, there is something called Hamming distance, there is Jarrow distance, there is least common subsequence. There are other kinds of algorithms. Needleman, Wunsch, and Smith-Waterman is extensively used in bioinformatics. BK tree metric is another tree-like algorithm. Soundex or Metaphone are very cool algorithms which are phonetic. So basically, it would try to match words which sound similar. So there are lots of resources available that anyone interested can look up, but these are pretty cool algorithms which are out there. Another cool source which I found was Record Linkage Toolkit. It's a library in Python which also does deduplication and tries to find similar records and links them together. And it is used, it can be used to do, again, deduplication, master data management, spell check, obviously. And it is also applicable in large data sets. For example, these techniques may not work for a huge, humongous corpus of text, but there are lots of cool methods which will work for large data sets. And yeah, hopefully it will. Can try it out. I tried out with different data sets, so hopefully this is of interest. And with that, I have also listed out a couple of things that I found useful while I was going through for this presentation. And this is the BITAP algorithm I was talking about. There are lots of Stack Overflow posts and Medium posts on fuzzy matching. So yeah, hopefully this will be helpful. So with that, I'm at the end of my talk, and I'm ready to take questions if you have questions.
Yeah, if anyone has any questions, you can put it into the chat. Or do you have an email that you could share with people, or LinkedIn?
Yeah, sure.
In case anyone wants to send you any questions afterwards.
Yeah, I am going to type out my email in the chat. And LinkedIn is, I forgot my LinkedIn. Let me just copy it.
Great, thank you.
No problem. Yeah.
And you're in Slack as well, aren't you?
Yes, I'm on Slack, yes.
Oh, we've got lovely messages here. One from Grace saying, thank you so much for your presentation and also providing awesome resources. And
Thank you.
This was great. Thank you. I look forward to implementing this.
Thank you.
And plus one for me as well. Such a great webinar, and I'm really looking forward to share this with our community afterwards as well.
Thank you, Sapphire.
No problem. Yeah, we have a few more. I want to say thank you for such an easy to follow presentation. Fantastic feedback.
Thank you all. And thank you for the opportunity to speak here. And yeah, feel free to reach out if you have questions. And I already shared my email and LinkedIn.
Thank you so much for sharing.
Of course.
And yeah, so again, everyone, we're going to share all of the resources on Slack, and the recording will be there as well. I'm going to finish today's webinar with the closing slides, but first I just want to say again a massive thank you so much. We really appreciate you coming today to volunteer for our community and delivering this fantastic webinar.
My pleasure.